new partner, Peter Thornycroft, thought Giles' dream ship should not be for cargo, but for the Navy. Frigates have traditionally been built long and thin. A long, thin hull can slice through the waves with minimum resistance, but in rough seas, this shape has its drawbacks. As the bow is thrust upward by an oncoming wave, the narrow stern slices downwards. The resulting seesaw movement, or pitching, both slows the ship down and stresses the hull. And rather like a floating pencil, the long, thin shape also tends to roll from side to side. Thornycroft-Giles' idea led them to an alternative frigate, much shorter and wider than usual. They built a large model so that it could be tested at sea, alongside a model of a conventional frigate. While that pitched and rolled in big waves, the new design sailed alongside almost level. With this shape, when a wave tries to push up the bow, the broad stern has more buoyancy to resist sinking. And being wider, it also resists sideways roll. The result, a much more level ride. The real surprise was that the short, fat ship could match the speed of the long, thin one. The secret lay in the shape of the hull under the stern. It had a flattened scoop in it. Conventional ships have a much more rounded shape. Giles badly needed hard scientific evidence, so he turned to the experts in ocean engineering at the Massachusetts Institute of Technology. Professors Paul Sklavounas and Chris Chrysostomidis are amongst the world's best. They helped design the hulls for America's Cup yachts.
I think it was about December or January that I met David Giles for the first time, and he had the fast ship design, and I was very impressed. Every about 20, 30 years, somebody with a good idea comes, and it happens, and then, of course, we say it's very obvious. We should have thought of it first.
Let me just draw a sketch of the fast ship. And they have a skeg that extends about all the way up here.
The hull looks good, but does the engineering make sense? Can it really be strong enough?
The first thing that we would like to be able to do is be able to predict the loads that the ship experiences when it's operating out in the sea. Now, this, of course, will be done in the computer environment because that is a quick and efficient way of doing it.
So how's it going, David?
Oh, it's going very well.
The loads and forces on the hull will depend entirely on how much it's tossed about in the waves. Here, in a computerized sea, they try to predict its performance at any speed and in all sea conditions.
It's nice to see how gently the flow detaches from the stern, which indicates that the design of the stern has been done very carefully.
You know, in general, this ship, compared to most ships I've been studying, has very little wave elevation. And the roll is generally less than 6.5 degrees. So it's very encouraging.
The computer predicts a smooth ride and reasonable forces on the hull. But testing a model in a computer is no substitute for getting it wet. At a test center in Sweden, Giles commissions a scale model that would sail under its own steam. In a month, he will return for the exhaustive tests that will decide if his name will go down in history as a pioneer of the seas.
The scale of the ship is 1/40th. And so the scale of the waves is 1/40th.
The model will run under its own power. It's linked loosely to the gantry above, which will track its every move. A sophisticated traveling laboratory, it can record the precise movements of the hull, detected by sensors embedded into the linking arms. Electric motors stand in for the gas turbines to provide power. In the first tests, the model meets head-on the roughest sea she's likely to encounter. Some of these waves are the equivalent of 20 meters high, and she's traveling at a scale speed of 40 knots.
She never slammed, never put her bow under.
The scale model pitches faster than the real ship, but cameras mounted on outriggers can slow the action to get a real idea of what a 230-metre-long fast ship might look like crossing the Atlantic.
The real ship will have to be measured. There'll be accelerometers and strain gauges along the hull. And in fact, probably for the first time ever, the decision on the speed may not be in the hands of the captain. There may be a speed reduction based on the input from all the different sensors in the ship. She even go on. What we wanted to do was to make her want to go in a straight line. And that's what we've done. So it's been successful.
They'll have to wait for the full computer results, but the evidence from the camera is looking good.
This is the really extreme condition. Do you see the way it explodes the sea? Exactly what it's meant to do. This is with the sea on the bow, so you've got quite a lot of roll in the motion as well as pitch. And there was some fear that there might be quite serious slamming there. Well, there you are, there's one. You see, you do get a certain amount of slamming there. The average roll angle in these conditions was about 5 degrees. Well, that's very modest.
Yes. You still have to consider what a regular ship would be going through on these kinds of conditions, and you'd be seeing rolls of
You see horrible things happening.
5 or 6 times that magnitude. Those are actually very stable operations.
Dave?
Yeah,
I have you on the speaker. Can you give me the news?
I just got the preliminary results, and at 40 knots, 7 meters significant wave height, head sea. No water was shipped on deck. The significant pitch was 0.7 degrees.
That's excellent.
So I think that slightly goes against traditional wisdom of naval architecture, doesn't it?
I know. It's very good news here.
Now that we've got the full results of the tank tests, we are very encouraged because first we've been able to take out 2 engines, which means a 25% reduction in fuel consumption, which is an enormous factor. The next point is that the seakeeping tests have shown that the loads on the hull were considerably lower than we'd anticipated originally, so we've been able to reduce the structure weight by about 1,000 tons. That is a huge impact on the commercial side. That's a wonderful result,